Hey there everybody, this is a video for my grade 1240S pre-calc students, and in this video we're going to be doing the first lesson of chapter 11. So in our last video we did this 10.3. That's the only chapter we're going to do in the only lesson we're going to do in chapter 10 for now. So that takes us to right here, and there is some algebra in this chapter, but for the most part it's all about counting. This is called the fundamental counting principle. So this is going to be kind of a longer lesson, so feel free to pause it midway and make yourself a sandwich, or if you're finding it really easy to follow and you could stand it being sped up, feel free to speed me up, make me sound like a chipmunk. But one way or the other, we're going to go through the fundamental counting principle, and here we go. You can choose one of three salads at a restaurant: a Greek, Caesar, or pasta, and one of three entrees: curry, hamburger, or sushi, from a menu. This is an interesting sounding restaurant. How many possible combo meals of one salad and one entree can you order? All right, well, let's just list them. I'll use the letters G, C, and P for the salad, and the letters C, H, and S for the entree. So I can get, I'll focus on the salads first. I can get a Greek salad and curry, or I can get a Greek salad and a hamburger, or I could get a Greek salad and sushi. There's all of the things I could do with the Greek salad. Then I could get the Caesar salad and the curry, or the Caesar salad and the hamburger, or the Caesar salad and the sushi. Or I could get the pasta salad and the curry, the pasta salad and the hamburger, the pasta salad and the sushi. So as you can see, there's 9 possible combinations that I can make. But this is a pain. What if there was 25 options for a salad and 13 options for an entree? What if there was also dessert options? We need a better method than making a list, and that's where we come across what's called the fundamental counting principle. If one task can be performed in A ways and another task in B ways, then both tasks can be performed in A times B ways. Take a look at the example we just did. There was 3 choices for salad, there was 3 choices for entrees, and 3 times 3 is, of course, 9. And this would work for bigger amounts of choices and for when you have more than 2 choices. For example, if there's 7 salads, 9 entrees, and 5 desserts, there would be 7 times 9 times 5 is 315 possible meal combinations. And clearly naming all 315 meals is impractical, and whoever wrote these notes has never seen the menu at a cheesecake factory. That thing's like a phone book. Anyway, your turn. How many license plates are possible in Manitoba? This is a classic problem. License plates in Manitoba have 3 digits and 3 letters. For now, we're going to ignore the possibility of a vanity plate where you pay money, I don't even know how much it is, to get whatever you want on your license plate as long as it's 7 characters or less. Most people have just your average, everyday, randomly distributed license plate, and those are all 3 letters followed by 3 numbers. And repetition can happen, so the first letter can be any one of 26 letters. Then the second thing can have any one of 26 letters. The third can be done 26 ways, right? So it could be A to Z, A to Z, A to Z. And then digits, there are 10 digits because 0 counts. So it could be 1 to 9 or 0, 0 to 9, 0 to 9. It is possible to have a license plate that's AAA111. So how many license plates are possible? Well, let's see. I would take my calculator. I think I'd type in 26 cubed and then put 3 zeros on it, which is 17,576,000 possible license plates. So as you can see, if Manitoba's population were to explode to the point where we had more than 17,576,000 registered vehicles, we would need another character on our license plate. And if you take a look at license plates from places like California or Ontario even, you will actually see that they have added another character to the license plate in certain areas. Number 2, how many ways can a store manager hire for 3 positions given 12 candidates? So there's 12 people and he needs to hire 3 of them. So there is 12 people that could get the job. Now here's what's different about this one than the last one. The first person he hires, there's 12 of them, but now he's hired one of them. He can't hire them again for another job. So now there's only 11 people to choose from for the second job, right? And then there's only 10 people to choose from for the third job. 11 times 12 is 132, so it's 132 with a 0 on it. All right, third example. How many outfits can you order if you have 4 choices of pants, 5 shirts, and 6 pairs of socks? And 4 times 5 times 6 is 120. And moving on to something a little more complicated, how many 3-digit numbers can you make using the digits 1, 2, 3, and 4, and 5 if you're allowed to repeat? So the first, you could have the 3-digit number 111 or 222 or 333. So there's 5 things the first digit could be, 5 the second, and 5 the third. So basically I'm just filling in those 3 blanks for the 3-digit number. There's 5 things it can be for the first digit, 5 for the second, and 5 for the third. So that's 125 possibilities. But in B, I'm not allowed to repeat digits. So I have 5 choices for the first digit, but now I can't use the digit that I used here. So in the next digit, it's only 4, and in the next digit after that, it's only 3. And notice that's considerably less than we had if repetition was allowed. Okay, so that's the fundamental counting principle. Now, let's talk about a shortcut. Before we get to this example, 6 people must be arranged in a row. How many different ways can this be done? Let's start with an easier example. You don't have to write this down, but how many different ways could I arrange 2 people? I'll call those people A and B. Well, the answer is 2. A goes first and B goes second, or B goes first and A goes second. That's it. There's only 2 ways to arrange 2 people. But what if I had 3 people? Persons A, B, and C. Well, I could go person A, then B, then C, or A, then C, then B. That's both ways where A's first. What if B's first? Then it's BAC or BCA. What if C's first? CAB and CBA. And we've run out of possibilities. There's 6. What if there's 4 people? What if I have person A, person B, person C, and person D? Now it's starting to get kind of large to try to list on a piece of paper. But let's just leave A first. A can go first, and then it's B, and then D, then C. Okay, that's all of the possibilities where A is first and B is second. So how about A is first and C is second? Well, that can be DB and, BD and DB. What about A is first, then D is second? And then that can be BC, or that can be CB. So I've run out of possibilities where A is first, and I got 6 of them. It makes sense that if I were to keep going with this, that I'd have another 6 for when B's first, and another 6 for when C's first, and another 6 for when D's first. So that's 4 times 6, which is 24. And thinking about it this way, let's think about it like that. There were 4 things I had to place, and I put the first thing I had to put, I picked the number A to go here, but I had 4 numbers I could pick from, or 4 people I could pick from. And then I had to put the next person here. I had 3 people to choose from. Now I have 2 people to choose from. Now I have 1 person to choose from. And notice this pattern. If I have 4 people to arrange in a row, I have 4 times 3 times 2 times 1. Notice this number here is actually 3 times 2 times 1. And this number here is just 2 times 1. And anytime I need to arrange a specific number of things, and the arrangement order matters, I have to go that number times the number that's smaller times the number that's smaller, and I keep going until I get 1. And that is called a factorial. 6 people must be arranged in a row. You could arrange them 6 times 5 times 4 times 3 times 2 times 1, which is 720 ways. And you write that. There's a shortcut for writing this called 6 exclamation mark. You say that as 6 factorial. So on your calculator, if you have this kind of calculator, I think it's shift 3 on this one. Yep. You'll see a little x squared. So if you want 6 factorial, you go second function 3, and there it is, 720, right? Which makes sense because that's 6 times 5 is 30, 30 times 4 is 120, 120 times 3 is 360, 360 times 2 is 720, times 1 is still 720. So this, whoops, what am I doing? So of course, 7 factorial should be 720 times another number times a 7. Because think about it, 7 factorial is kind of like saying it's 7 times 6 times 5 times 4 times 3 times 2 times 1. But notice this part I already know is 6 factorial. So it's really just 7 times 720, which is 5040. That is the problem with working in pen. Okay, so like I said, let's double check that our calculator knows this. 7 factorial. And look at that, I don't even need to hit equals on this calculator. Most calculators you do need to hit equals. If you're using this kind of calculator, first of all, it's not shift 3 on this. I think it's shift 4. Yep. And they use a different letter. They use n instead of x. But notice the exclamation mark is what tells you it's factorial. So 7 second function 4, and this time it actually gives you the little exclamation mark, and you have to hit equals, and there it is, 5040. If anybody's using your older brother or sister's graphing calculator that got handed down to you, or maybe your parents picked you one of these up because you're also in applied math, it's actually a little harder to find on these things. It's not on the main keys. You have to find it. 7 factorial would be 7, then you hit math, then you go over to probability. And it should make sense that it's in probability, because notice the number of ways you can do things is very important to the world of probability. And then you pick 4 on the menu, and there you go. So it's a bit of a drag to get to on the more fancier calculators, actually. So there we go. Feel free to message me if you can't find factorial on your calculator, and we'll work it out for you. This one I can do without a calculator. 4 times 3 times 2 times 1 is 24. And this one, well, I'm definitely going to need a calculator for that. 18 factorial. So I'm going to go back to this guy. So that's 18 second function 4, and check that out. Does everybody remember what that means? Here, if you did it on this calculator, it would look like this. 18 factorial. What does that mean? Well, this calculator gives you a bit of a hint, right? It is not. This calculator is misleading. It is not this number to the power of 15. It's actually this number times 10 to the power of 15. It's what we call scientific notation. You've seen it, I'm sure, in your science courses. And what it means is that this number doesn't fit on the screen, so they've shortened it, but this decimal is actually 15 places to the right. So it's a 16-digit number, and of course this thing can only hold 10 digits or whatever. So it's about, I'll just round it, 6.4 times 10 to the 18. What kind of a number is that? 15, not 18, 15. There we go. And what kind of a number is 10 to the 15? Well, 10 to the 6 is millions, so 10 to the 9 is billions, 10 to the 12 is trillions. What comes after trillions? I want to say quadrillions, is that right? So this is 6.4 quadrillions. That is an amazing thing to think about. If you had a class with 18 kids in it and you wanted to line them up in a row, how many different ways can you do it? It's this enormous number, far bigger than the number of people on the planet. It's really amazing to think when you're using factorial how quickly the numbers get enormous. In fact, I think on your average calculator, I think 69 is about the biggest factorial you can do. 69 factorial. And there you go. 1 times 10 to the 98. If you want a number that's bigger than 10 to the power of 100, I don't think these calculators can handle it. So let's try it. 70 to a factorial. Error 2, overflow error. I think this one would be the same way. I think the big fancy grapher can go a bit bigger because it's got a little more power to compute here. So let's see, what is 70 factorial? Let's see, does it give it to us? No, overflow. So that's it. That is as big as it can go. I think if you were to open up your Windows calculator, you can go bigger on this thing. So let's see. So and factorial's on here too, somewhere. Where's factorial? Oh, there it is, in factorial. So if you did 70 factorial, let's see. Well, there you go. 1.19. So it's a 101-digit number. Isn't that lovely? Okay, so very cool. Anyway, in general, we define the factorial notation for n, any number, as an element of natural numbers, right? We don't talk about factorials of negatives. We don't talk about factorials of decimals or fractions, at least not in this course. So any number written as a factorial is itself times the next number that's smaller, times the next number that's smaller, all the way till 1. So also, we define 0 factorial as 1, and it's something that we say is a definition, and it's not based on proof. What we mean by that is, if you remember back in grade 9, we convinced you, hopefully, that any number except for 0 itself, any number in the universe except for 0 to the exponent 0 has to be 1, and we can prove that to you. There's a number of ways I can do it. I can do it just by showing countless examples, right? I could make a series of examples that I know would be exhaustive, so it would work for all examples. So say I had 2 to the 4 divided by 2 to the 4. Well, that's 16 over 16, which is clearly 1. But I also know that my exponent laws mean that I can subtract those, and I also get 1. So since this thing equals 1, and it also equals, since this thing equals that thing, and this thing is equal to 1, then these two things must equal each other. That's the gist of the proof. So there's a proof for that, but this one here is more of a definition than a proof. There's lots of cool videos on the internet. I could maybe put the link to at least one of them on the blog, but I'm not going to go into why the argument can be made that this has to be true. So we're going to just accept it as an axiom, as a fact. So 0 factorial is 1. 1 factorial is also 1. 2 factorial is 2. 3 factorial is 6. 4 factorial is 24. But once they get bigger, we need a calculator. Now, be careful, though. Just because we need a calculator to figure out what 11 factorial is, I certainly have no idea off the top of my head what it is. It's pretty big. It might, again, be so big that my calculator needs to do it in scientific notation. But I can still do this without a calculator because, check this out, 11 factorial is like saying 11 times 10, and then times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But 9 times 8 times 7, starting from here, really starting from anywhere, it's another factorial. So if I'm dividing by 9 factorial, they cancel. So it's 110. See that? I don't actually need a calculator to calculate simple, simplifiable factorials. And let's do another one. 5 factorial over 7 factorial. So that's 5 factorial over 7 times 6 times 5, 4, 3, 2, 1. And 5, 4, 3, 2, 1 is 5 factorial. Bye-bye. So that's 1 over 42. Okay, and now we can do algebra with them too. Think of this again. N factorial is whatever n is times the number that comes before n, which I could call n minus 1, times the number that comes before that, which I can call n minus 2. And anywhere I want to stop, I can just slap a factorial on it, and then it would go till it gets down to 1. So I'm going to write n factorial as n times n minus 1 times n minus 2 factorial. And that allows me to cancel the n minus 2 factorial on the bottom, because anything divided by itself is 1. So this is just n times n minus 1, or if you want it in expanded form, it's n squared minus n. This one, think about this one. If what I just did there made lots of sense to you, pause the video and see if you can simplify that. Did you try it? N plus 1 factorial is n plus 1 times the number that comes before n plus 1, which would be n, and then factorial. So this is just n plus 1. Isn't that cool? Okay, so if that makes sense to you, and hopefully it does, then what we're going to do next is we are going to show you a little proof here that we can do with factorials. Prove that 5 factorial minus 3 factorial is equal to 19 times 3 factorial, and no, don't work these out as numbers. I guess you could. You could prove this by just saying that that's, what is that again? 120 minus 6, which is 114, and I guess that's what 19 times 6 is. That's inelegant. I am going to write 5 factorial as 5 times 4 times 3 factorial. And notice I'm taking the left-hand side here. Okay? Then I'm going to factor out 3 factorial, leaving me with 5 times 4. And when you factor something out of itself, it leaves behind 1. So that's 3 factorial times 20 minus 1, which is equal to the right-hand side. Oh, that's way prettier than actually working those out as numbers. All right. They didn't give you a whole lot of room for this one, but notice that if we can do algebra expressions with factorials, that means we can solve equations with factorials too. So we're actually trying to figure out what n is here. So same trick I used in example C and D above. N factorial is like saying n times n minus 1 times n minus 2 factorial. And there's people going, how did you know to stop there? Why didn't you go n minus 3 and then slap a factorial on that? Well, because I'm trying to simplify this thing, and I notice n minus 2 factorial is what I have on the bottom that I'd like to cancel. So I have n times n minus 1 is equal to 30. And you could probably just do that mentally. A number times a number that's 1 smaller is 30. And I know they have to be whole numbers, right? Or natural numbers, right? They can't be negatives. They can't even be zeros. So they certainly can't be fractions or decimals either. So what whole number times 1 smaller is 30? Yeah, it's 6 and 5, so n is 6. But if you couldn't figure that out just by kind of eyeballing it like that, you could expand this and turn it into a quadratic and factor it. And if you factor this, and I'm kind of out of room here, notice that that answer there would lend me to the answer, that of course equals 0. I forgot the rest of my equation. That of course lends you to the answer n is -5, which can't be. Again, we have to be in natural numbers. We can't be in integers. So this is an extraneous answer, and the right answer is just n equals 6. Cool. So there's some algebra with factorials. You'll have some of those in your homework. And now we're getting to something we call permutations. A permutation is an arrangement of objects where the order of the objects is important. Okay? So an arrangement is a set of objects in which the order of the objects is important. It's called a permutation. For example, how many ways can you arrange 4 people sitting on a bench? That's a permutation, and the answer is 24. Whereas, how many ways can you choose a group of 4 people from the class is not. Because notice I didn't say that you have to choose the tallest kid first, then the second tallest, right? Order doesn't matter in this example, so it's not a permutation. Permutations are where order matters. And this leads me to the thing in the education system that bothers me the most. If you're wondering, well, what's the math of things where order doesn't matter? If how many ways can you arrange 4 people sitting on a bench is a permutation, what do you call how many ways can you choose a group of 4 people from the class? Well, that's called a combination. Permutations, combinations. In fact, why don't we just jump ahead a little bit? I've learned real early in my career that if you want to teach kids something that is easy to confuse with something else, don't introduce them on separate days or a week apart. Introduce them at the same time. That sounds counterintuitive, but it actually does work. It totally works with surface area and volume at junior high, right? I think if you learn them both or look at them both for the first time at the same time, it actually is easier to keep them apart. So let me just jump to lesson part 7 here, which we won't get to in this lesson. This will be how we start the next lesson. But there it is. A combination is a selection of objects where order doesn't matter, right? So for an example, if I have students A, B, C, and D, how many different groups of 3 could I pick? And a group that's ABC isn't a different group than ACB. It's just a rearrangement of the same 3 people or 3 objects. So that's called a combination. How many different groups can I pick? Permutation is how many ways I can make arrangements. Okay? And this is where I get to, like I said a minute ago, the thing about the education system that has bothered me the most ever since I was in high school. Why do we call this a combination lock? It is not. It should be called a permutation lock. Because if your combination on this thing was, say, I don't know, say that your combination on this thing was 12, 7, 35. If you came up and did 7, 12, 35 or 35, 7, 12, would it open? No. So order matters. It should not be called a combination lock. It should be called a permutation lock. I don't know why. It's English. All right, anyway. Permutations have a lovely, easy to use little formula. I'll put a nice little circle here, a cloud around it. And here's how it works. If you have n distinct items and r items are taken and arranged, then the number of permutations is what we call NPR, or Nperm-R, which is, or n permutation r, I guess if you want to be formal, which is n factorial all over divided by n minus r factorial. So for example, if you wanted to arrange 3 books in a display case and you have 7 books to choose from, that's 7 permutation 3, which is 7 factorial over 7 minus 3 factorial, which is 7 factorial over 4 factorial. And once again, they just use the little shortcut. That's 7 times 6 times 5, and then slap a factorial on the 4, cancel those 4s, and then they got just 7 times 6 times 5, which is easy to figure out, 210. Now, point out that I could have done this using just the counting principle too, right? I have 3 books I want to arrange, and I have 7 to choose from. Well, I want to arrange 3 books. 1, 2, 3, right? There's 7 things I could pick for the first book. There's 6 things I could pick for the second book. There's 5 things I could pick for the third book, which is exactly what we got. Having said that, these questions will start to get complicated to the point where it'll be easier to use this formula than to use the counting principle. The formula is a shortcut for all the counting you'd have to do to get to the counting principle once the questions get more complicated. So, number 1, let's just see if we can work the formula. that is going to be 6 factorial over 6 minus 4 factorial. I wouldn't let you use a calculator for this one. That's going to be 6 times 5 times 4 times 3 times 2 all over 2 factorial. Notice 2 and 2 factorial are the same thing, so I don't bother with the factorial on there, right? 2 times 1 is the same as 2 times 1, so they're gone. And this is going to be 30 times 4 is 120. 120 times 3 is 360. There we go. All right, so there's the first one. Now the second one is going to be more algebraic. I know the permutation value. I'd like to figure out the n in the formula, and this is what I'm going to do. It's n over n minus 2 factorial equals 30. Look familiar? It's the one we did in the last page. So I'll just say see last page. And n is going to be 6. And this one here, all right, this one's going to take a little more thinking. This is n factorial over n minus 3 factorial equals 120. Now, I'm going to expand that, and I'm going to expand it into n times n minus 1 times n minus 2 times n minus 3 factorial. That is what I'm going to turn n factorial into. So once I do that, this n minus 3 factorial, here, I'll just write it out. Thought I could save some room, but I cannot. Okay, so that is going to cancel the denominator. Those make 1. So now I have a number times 1 less than that number times 2 less than that first number is 120. Now, you might be going, what, am I going to multiply all that out and solve a cubic? No, you're going to guess and check the way we did back in Unit 1 when we were trying to find zeros of polynomial functions. Remember that? What do I know here? I know that n can't be a fraction or a negative. So let's see. Maybe it's 5 times 4 times 3 is 120. Nope, too small. Maybe it's 6 times 5 times 4 is 120, and bingo, it is. So n is equal to 6. Really, that's all that you have to do in a question like that. You can do a little bit of guessing and checking. Do not expand cubics, please. All right, number 4. You have 7 basketball players, and there's 7 places on the bench. How many ways can you arrange the players? Now, do you notice why now the formula is going to be easier than this? I don't really want to write out 7 blanks and start multiplying all those numbers when all I have to do is 12p7, right? I have to choose 7 things out of 12 and arrange them. So that's going to be 12 factorial over 12 minus 7 factorial. And that's going to be 12 factorial over 5 factorial. Okay, I need a calculator for that one because 12 times 11 times 10 times 9 times 8 times 5 or times 6 is too big a number to play with in my head. So I'm going to punch buttons, and while I'm at it, I'll actually show you an even quicker shortcut. But first, 12 factorial divided by 5 factorial is, and that's a big number. There's a lot of ways the coach can arrange that bench. Coach would spend the rest of his life trying to figure out how to arrange that. That's 3,991,680 ways to arrange those players. Okay, now that we know what the number is, check this out. If this is the formula right here that I want to do, there is on most scientific calculators, there it is right there. Can you see that? That formula is on the calculator. So I can just enter 12 permutation, or is it again? Permutation 7, and it even gives you a little p number to let you know that you're using the permutation formula. And isn't that nice? Even the cheaper calculators tend to have that. They might not actually have a p come up on the screen, but yeah, there it is. It's shift 9 on this one. So what was my calculation again? It was 12 shift 9, and that puts it in permutation mode. These calculator doesn't give you any hint that you're in permutation mode, and then hit 7, and then there's that number again. But it's still there. Again, if there is anybody rocking one of these things, it's in that math probability menu, because this is, again, a probability issue thing. So 12 math probability, and it's the second choice. It's number 2. 2. So there you go. 12 perm 7. Ta-da! And there we go. Okay. So that's permutations. Next, we're going to be going to, let's see here. Hang on. My pages are all disorganized. Yeah, that one can go up there. So this is a very exciting part of the video as I shuffle through pieces of paper so I don't get it mixed up. There we go. Sorry. Okay. Permutations with repetitions. Imagine that the letters of the word book are written out on tiles. I actually imagine that they're on like Scrabble tiles. Ever play Scrabble? So suppose I have them on tiles. Now, how many ways could I arrange them? Even if some of them don't make actual words, how many ways can I arrange them? And Ms. Cox, when she put these notes together, noticed that Kobo is a permutation of the word book, which is very clever marketing. Anybody have a Kobo, one of those electronic book reader things? Anyway, Kindles too. It's like a Kindle, only it's just a competition for a Kindle. So oddly enough, that Kindles are way more popular than Kobo. So I think the Kindle was, even though the clever marketing here wasn't clever enough to beat Kindle. But anyway. Okay, how many different ways can I arrange it? Well, notice that I'm going to have to kind of say that I have two O's here, right? I can say that I'll take the word book, so the first one is just the way it is, and then, well, I actually didn't mean to make this O smaller than that one, but that actually helps a little bit. I'm going to call this the O1 and O2. If I just go now O2 and O1, there we go. Now, if I just mix up those two tiles, if you weren't looking, could you be able to tell that I switched the tiles? No, they look the same. This is the same word again. And then same problem here. If, say I go B-O-K-O, and I'll say that's my first O and my second O. Well, I could also have the word B-O-K-O where that's my second O and my first O. There's no way to tell the difference between those two words. My last pair here is B-K-O-1 and O2, and then B-K-O2 and O1. And so notice that's just 6 ways to do it with the B first, and again there's 4 letters to choose from, so etc., and you should get 24 permutations. But notice that there's 12 pairs that are the same. This word and this word are not going to be any different. This word and this word are going to be the same, and these 2 words are the same. So it's actually 24 divided by 12, which is, or sorry, not 12. That's the answer. It's 24 divided by 2 factorial, which is actually going to be 24 divided by 2, which is 12. In general, notice this says the same thing we just talked about, right? If you switch the O's, you still have the same word. So, how many distinct permutations do you have? Well, that's 4 factorial divided by 2 factorial, which is 12. Now, where does this 2 factorial, where did I get this from? It is the number of objects that are the same. So it's number of ways to arrange the identical objects. So, in general, if you have a set of n objects with a objects that are identical, your arrangement total, your number of total unique permutations, that's another good word for distinct, is unique, right? Because the word book and the word book, there's nothing unique about either of these if you switch the O's. So in general, a set of n objects with a objects that are identical is n factorial divided by a factorial. And if there's more than one thing that's identical, you would just keep dividing by the number of ways to arrange those unidentical things. So let's do a couple of examples like that. Manitoba has 8 letters. If I was playing Scrabble, that's an 8-letter word. And there is 2 A's. So every place that I put an A, I could put one of 2 things. So I have to go 8 factorial divided by 2 factorial, which is 20,160 when I punch buttons. Now, suppose I make a number using the digits 81818. Well, if I just switch the 8s, you can't tell the difference. If I switch the 1s, you can't tell the difference. So there is 1, 2, 3, 4, 5 digits here. And there's 3 identical 8s. Identical 8s. And there is 2 identical 1s. So that's going to be 5 factorial divided by 3 factorial, 2 factorial. This one I think I can do without my calculator. That's going to be 5 times 4 times 3 factorial divided by 3 factorial times 2 factorial. Those 3 factorials cancel. 2 factorial is just 2. 2 goes into 4 twice, so my answer is 10. Notice that the number of ways I could actually arrange 5 things is, what is 5 factorial again? 120. But only 10 of them. There's actually only 10 unique arrangements because of all this repetition. Cool. All right. This doesn't look like it's the same kind of problem, but actually it is. This is a neat question. I like this one. How many different paths can you follow from A to B if you can only move up and right? Well, this is kind of cool. So you're only allowed to go up and right. You're not allowed to go up, right, then down, and then back over and up. You're not allowed to go past where you want to go and then back to the left. You're not allowed to go down or left, just up and right. So I can get to this point only one way, right? I have to go up. I can't go that way, and back because I'm not allowed to go left. So there's only one way to get to this point. And by the same logic, there's only one way to get to this point, and there's only one way to get to this point, right? How many different ways can I get to this point? Okay, well, let's think about that. Once again, I'm not allowed to move down, only up. So I can't go this way, then down. I can only go that way. So there's one way to get to here. There's one way to get to here. There's one way to get to here, one way to get to here, and one way to get to here. All right. Now, how many different ways can I get to this corner? Notice the answer is 2, because I could go up and then right, or I could go right and then up. 2 paths. How many different ways can I get to this corner? Well, notice that there was 2 ways to get to this corner and 1 way to get to that corner. So altogether, there's 3 ways I could get to that corner, right? I could go that way and up, or I could go that way over and up, or I could go that way and that way. 3. And how many ways could I get from, say, this to this corner here? Well, there's 3 ways to get to here, 1 way to get to there, so that's 4. How many ways are there to get to this corner? Well, there's 2 ways to get here, 1 way to get here, so that's 3 again. But how many ways are there to get to this corner? Well, there's 3 ways to get to there, 3 ways to get to there, so there's 6 ways to get to there. Do you see the pattern yet? Basically, all I have to do is add, to get this corner, the 2 diagonals that are adjacent to it. So if there's 4 ways to get to here, 6 ways to get to here, there's 10 ways to get to there. If there's 3 and 1, this one's 4. 6 and 4, there's another 10. 10 and 10, that makes this one 20. 4 and 1, that makes this one 5. 5 and 1, that makes this one 6. And 10 and 5, there's 15 ways to get to this corner. 6 and 15, there's 21 ways to get to that corner. And 20 and 15 makes 35 ways to get to that corner. And now I can answer the question. To get to point B, there's 35 plus 21, which is 56 ways. Thank goodness this wasn't a much bigger problem and a much bigger array of corners. Would you like to see the shortcut? Notice that no matter how I get to this corner, I had to go up 3 times, and I had to go right 1, 2, 3, 4, 5 times. Every single one of the 56 paths that make it to there have 3 ups and 5 rights. So there's 8 moves altogether. There are 5 rights and 3 ups. So it's basically like the exact same type of question that if I had these letters in Scrabble, how many different ways could I arrange them and have them unique? So that's going to be 8 times 7 times 6 times 5 factorial all over 5 factorial times 3 times 2 times 1. I'm not going to bother timesing 1. That cancels that cancels that. And the answer is what we already knew, 56. Cool, huh? These kinds of problems, of course, lend themselves to things like network connection problems. So factorials and permutations are a big part of that kind of combinatorial math. Now, permutations with constraints. What do we mean by constraints? I'm actually working on a textbook example here. And you can follow along in the textbook if you find what I'm doing kind of confusing. But basically, it works like this. 5 people, A, B, C, D, and E, Andy, Brian, Calvin, Daniel, and Eugene, are seated on a bench. How many ways can they be arranged if Eugene has to sit in the middle? He just has to. He's difficult, that guy. So I can kind of just think of this as, all right, there's only 5 seats. 1, 2, 3, 4, 5, and Eugene has to be in the middle. So there's only one way to place that spot. There is, however, 4 ways I could put that, because remember, I'm not putting a 5 there because, you know, Eugene's already here. But that's 4 other people that I have to choose from to sit there. Now that I put one of them there, 3 people could sit there, 2 people could sit there, 1 person could sit there. Overall, that's 24 possible ways to do this. Now, A and B must sit together. Isn't that interesting? So I want to arrange 5 people on a bench, but my rule is, my constraint is that I can't separate A and B. They have to be next to each other. So basically what I do is I treat A, B like one object. And yeah, in math we're all sociopaths and we treat people like objects. We just count them. So treat AB like one object, which means that I'm only, instead of seating 5 things, I'm seating 4 things, right? And AB could go there, AB could go there, AB could go there, AB could go there. So there's basically 4 times 3 times 2 times 1. But wait a minute, it doesn't say that A has to be on the left and B has to be on the right. It could be AB or BA. So AB could be here or BA. 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 So it's actually 4 factorial times 2 factorial, which is the number of ways I can arrange those 2 people. So that's actually 4 factorial times 2 factorial, which is 48. See if you can make sense of that. Now, this is interesting. A and B must not sit together. A and B don't get along. If you sit them next to each other, they'll start a fight. So there always has to be at least one person between them. Guess what? Rather than try to count all the ways to kind of separate them, like they could be separated by 1 person or by 2 people, I got a better idea. The total number of ways to sit 5 people on the bench is 5 factorial, and the number of ways that I could seat them where A and B sit next to each other is 48. So subtract 48, and the remainder must be the number of ways where they are not sitting together. Boy, that makes life pretty easy. So that's actually 120 minus 48, which is 72. Cool. All right, if this stuff's making some sense to you, pause the video and give these 3 examples a try. I'll wait. All right, did I wait long enough? Did you give them a try? How many ways can you arrange the books if not restricted? So I have 3 calculus books, 5 biology books, and 4 different economics books. But I don't care if it's a bio, then an economics, then another economics, then a bio, then a calculus. There's no constrictions, no restrictions whatsoever. So it's just, there's 12 books, factorial, and this is a huge number. It's 479,001,600. That's a lot of ways to arrange 12 things, but that's the way it works out. How many ways can you arrange the books if they must be arranged by subject area? So there is 3 calculus books, but they have to be together. So I could have ABC or BAC, or you get the idea. It's 3 factorial. Then I have to keep the 5 biology books together. Then I have to keep the 4 economics books together. But it doesn't tell me what order those categories have to be. It doesn't say that it has to be calculus, then biology, then economics. It could be economics, then calculus, then biology. So there is, of course, 3 factorial ways to arrange the subjects. So the final answer then is going to be, I punched this out already, 103,680. Notice that's quite a bit smaller than that. Now for C, this is one of those cases where I don't know what they meant in this question. It says, how many ways can you arrange the books if all the calculus books must go on the right? Now, does that mean it's like B, where they're arranged by subject, but that subject of calculus has to be on the right? Or do they mean like it's an A, where I don't really care, except everything else can be willy-nilly, but the 3 calculus books have to be on the right? Willy-nilly is an expression your generation has not embraced yet. It just means chaotically, randomly. So, which one do they mean? All right, well, I don't know, so I'm going to solve both. So, if other subjects don't need to be together. Then I have 9 books to arrange that can be in any order, times 3 factorial that all have to be on the right. And that's a huge number. It's 2,177,280. Punch buttons if you don't believe me. And then if I solve it the other way, if the other subjects are still grouped. All right, so there is 5 factorial ways to arrange the biology books. There is 4 factorial ways to arrange the economics books. And then, of course, the 3 calculus books have to be on the right, and they can be arranged 3 factorial. But I have to times this by 2 factorial to take into account the fact that it could be economics then biology or vice versa. So there we go, and that's going to be, what do you think? Is this number bigger or smaller than that? It's got more things times together, but yeah, it doesn't get nearly as big in terms of factors. So this is actually way smaller. It's only 34,560 actually. Let me double check that. That seems, is that right? Let's see. Here's how I'd punch that. I'd go 5 factorial times 4 factorial times, I know 3 factorial, 6 times 2, and yep, there it is, 34,560. Right? And this one, if I was punching buttons, I would just go 9 factorial times 6. Boom. Look at the difference in how big that number is. Cool. So that's constraints. Next is cases. Every example we've seen so far is a permutation with one case. I was able to do the calculation in one step. But sometimes it's impossible to summarize all possible permutations into a single equation. If you cannot summarize a situation, you must break that situation into distinct cases and add the resulting permutations for each case. Example, I have the letters A, R, T, E, F, Q, U, and again, think of them as being Scrabble tiles. And I have to put them in a row on my little wooden block that I put the Scrabble tiles in the game. But the arrangements must begin and end with either both consonants, so it's either R, T, F, and Q at the front and back, at the left and right, or it has to be front and back both vowels, and the 3 vowels they give us are A, E, and U. Now, why can't I do this as one calculation? Well, because either I have to have a consonant at the front or back, or a vowel at the front or back, and there isn't an equal number of those two things. So let's write this out. There's 7 places to put my letters, and I have to put R or T or F or Q here. So there is a 4 possible things I can put there. Now, once I put one of my consonants here, I have to put the other one here. So that's R, T, F, or Q minus 1 because I already used one of them on this side. Now, there's still 5 tiles for me to place, and I can place them in any order I want. So 5 times 4 times 3 times 2 times 1. So it's actually going to be, this is 5 factorial in the middle times 4 times 3, which is 1,440 possible arrangements. That's just case 1. Case 2, they begin and end with vowels. Now you're going to see, isn't it going to be the same as this but times 2? No, it's not. Because there's only 3 things I can put here, A, E, or U, and then over here, A, E, or U minus 1 of them. So 3 things could go there, 2 things could go here, and then there's still 5 tiles for me to place between them. Notice that is a different calculation. It's not 5 factorial times 12. It's 5 factorial times 6. So it's actually 720. So in sum, there is 1440 plus 720, or 2,160 possible ways to arrange these letters. Okay. If that made sense to you and you want to try it yourself, feel free to pause the video and try this example. All right, how'd it go? How many different 3-digit even numbers, make sure you understand even, greater than 303 can you make with 1, 2, 3, 4, 5, 6? You're not allowed to repeat the digits. Case 1 is that you end with a 2. Right? Because remember, even means that you have to end in the 2, the 4, or the 6. So case 1, you end with a 2. You're making 3-digit numbers, and this has to be a 2. So there's only one 2. But this can be anything. Oh, wait a minute. It can't be anything, can it? Oh, yeah, it has to be bigger than 303. So it can't be the 1. And I know it can't be the 2 because the 2's already here. So this can actually be the 3, the 4, the 5, or the 6. So there's 4 things that can go here. And then, of course, there's 6 digits. I've just used 2 of them. There's still 4 left. So that's 16 ways I can do it for case 1. For case 2, I end with a 4. Okay. Now, if a 4 has to go in this last spot, so there's one thing that can go there, notice that this isn't a 4 this time, because I can't use the 4 in the first spot like I did here. It still has to be bigger than 303. So it can start with a 3 or a 5 or a 6. It can't start with a 2 or else I wouldn't be greater than 303. So this is 3 times 4 times 1, which is 12. And in case 3, ends with a 6. And notice this one will be actually the same as that one. I can end in either 3 or 4 or 5, but the 6 has to go here. So there's one way to do that, and then there's 3 ways to do that, 4 ways. And so that's 16 plus 12 plus 12. Total that up, and the answer is 40. How'd that go? All right, let's do more examples like this. And again, feel free to pause the video and try it yourself before I run through it and see how it goes. Okay, how many different 3-digit multiples of 5 are possible using the digits 0, 2, 3, 5, and 8? And again, we'll assume no repetition. So case 1, what do you think case 1 is? Case 1 will be that we end in, I'll say a 5, right? Because if you're a multiple of 5, you have to end in either 0 or 5. The only numbers divisible by 5 end in 0 or 5. So in case 1, we're going to end in a 5. Right? Which means that this could be a 2 or a 3 or an 8, because we have to be, well, you know, we can't put a 0 out front, or else if you put a 0 out front, it's not a 3-digit number. Technically, it'd be a 2-digit number. So this is going to be 3 times 3 times 1, which is 9. For case 2, we put the 0 at the end. Right? There's, oh, oops. Sorry. Put the 0 at the end. There's only one way to do that. And then this can be either 2, 3, 5, or 8. Notice this has one more choice than that one did. So that's why we have to do them as 2 different cases. We can't just times the 9 by 2, because case 2 has 12 ways to do it, and that's 21. All right, number 2. How many 3-digit numbers greater than 400 are possible if I'm allowed to use the digits 1, 2, 3, 4, 5, 6, and 7? All right, how many of the 3-digit numbers are greater than 400 are possible? Okay, well, this one's actually pretty easy. It doesn't say that it has to be odd or even. It just says it has to be bigger than 400. So I could start with a 4, right? So it could be a 4, 5, 6, or 7 in that first spot. And then there's still 6 digits to go, and then 5 digits after that. So there's 120 possible numbers I could make that fit that constraint. Now, how many of these numbers are odd? Okay, well, odd numbers either end in 1, in which case that means that that's basically this calculation here, more or less, right? It's 4. There's 4-digit numbers that can go there, right? It can be either 4, 5, 6, or 7, right? Because it still has to be bigger than 400. And the last digit has to be a 1, so there's only one way to do that. And there were 7 digits in the first place. I used 1 there and 1 there, so there's still 5 to go. So that's 20 for that case. For the next case, it could end in a 3, right? Odd numbers, remember, odd numbers end in odd digits. So if it ends in a 3, this is actually going to be the same, right? It's 4, 5, 6, or 7 here, only it ends in a 3 instead of a 1, but there's still only one way to do that. So it's still going to be 4 times 5 times 1, which is 20. What'll be different is if we calculate the possibility that it ends in a 5, because now I can't have 5 in that first digit place. So there's actually only 3 things to choose from for the first digit, 5 for the second, 1 for the third, because again, that last one has to be a 5. And that's going to be 15 possibilities. And then that it ends in a 7 is going to be the same mathematically as if it had ended in a 5. So there we go. 20 and 20 is 40, 15 and 15 is 30, add it all together, 70 possible outcomes. And that gets us to where you can now do the 11.1 assignment in the assignment book. Okay, so next lesson in a couple days. Thanks for watching.